Okay, so welcome everybody. My name is Yunlong, and I'm a PhD student at Robotics and Perception Group. And today I would like to talk about my research on reinforcement learning and its application to drones. So, as you have seen from Antonio's presentation, like drones are super agile robots, and it can navigate through narrow spaces in a very agile and fast motion. And the motivation of my work is to develop intelligent system that one day can fly as good or as faster as human pilot and also more robust than human pilot. And this is very important because then we can deploy the system on time critical tasks, like for example in search and rescue, and you want to search for the people in a very fast manner. And my focus is using reinforcement learning because reinforcement learning has shown to be very useful in solving very complex tasks, for example, the game of Go, and also for solving robotics tasks. And in today's talk, I'd like to focus on two of my recent work. One is about learning time optimal trajectories using reinforcement learning, and another one is policy search for motivative control, which is a way to combine the policy search and advanced control theory like MPC. So learning time optimum trajectories. Suppose given the perfect knowledge of the environment, we can define a list of waypoints which connects the open space. And given this waypoint, the question is, what is the time optimum trajectory that can travel through all these waypoints? And this trajectory has to be dynamically feasible through all these waypoints, and also has to account for the actuator constraints. It also has to scale to the environment, arbitrary complexity, and also robust to the environment uncertainties. So in robotics, there are some related work. For example, the first one is one of the very well-known minimum snap trajectory. And this trajectory can be computed very efficiently, but it doesn't feature any time optionality of the task, which is not optimal solution for some tasks, for example, in drone racing. And on the other hand, there is Alpha Pilot from our group in 2020. And there, the task is to find the time optimal trajectory from point A to point B and also go through all the gates. And there, they use simplified model of the quadrilateral as like kind of point mass model. In this case, you can compute the time optimal trajectory between two states in a closed form solution. And then by combining with dynamic programming, you can find the optimal path through multiple waypoints. But here, the assumption is like the quadrilateral is point mass model, which is not realistic and also not dynamically feasible. And it makes the low-level controller very difficult to track such kind of trajectory. And finally, there's this work of CPC, complementary progress constraints for time optimal trajectories. And this work makes use of nonlinear programming for the trajectory optimization. And it can find the time optimum solution, but it relies on quite expensive trajectory optimization and doesn't scale to very large and complex environments. And the motivation of my work is to solve this problem using reinforcement learning. And this is essentially a very difficult task for reinforcement learning because in reinforcement learning, you have to trade off between exploration and exploitation. And this is like long horizon planning problem. And what we propose is using model-free reinforcement learning. And model-free reinforcement learning, you have to define a policy, and the objective is to maximize some form of reward function. And by maximizing the reward function, you can find the optimal policy for the task. And in our task, we define the policy as kind of a neural network policy, which is a multi-layer perception. And the input to this new network policy is the state of the zone, including the velocity, acceleration, orientation, and body weight. And in addition, we also put the gate observation as the input of the new network. And the output of this new network is the rotor thread, which in this case, we can fully exploit the potential of the platform because we don't rely on any lower dimensional, low-level controller. And the objective of our task is to minimize the time, but the time is a sparse signal, which makes it difficult to minimize the time directly. And instead, what we do is maximize the progress along the track, along the path connected between multiple waypoints. And the training, during training, we make use of like parallelized sampling and also distributed initialization. As you can see from this animation, we simulate several hundreds of quadrilateral in parallel, and also we randomly distribute this quadrilateral along the tracks. In this case, we can collect as many samples as possible and also cover as much space, the state space as possible, and you can have better estimation of the policy gradient. And we can learn this policy very efficiently. Once we obtain this new network policy, by combining with the dynamics of the quadrilateral, we roll out the trajectory for let's say like 10 seconds of such trajectory. And we evaluate our approach on different environments. For example, in here, we have 3 different kind of tracks. On the left-hand side, we have this alpha pilot, and in the middle, we have this split S, and we also have this very large, long AirSim tracks. And these 3 tracks has different complexity and also different length. And we compare our approach against the 2 baselines. One is the polynomial, which is very naive baseline, doesn't feature any time optimality. And the second approach is this optimization-based approach, like this CPC I talked before. And this one computes the time optimum solution. And we show that our approach, like this neural net policy, can actually achieve very good performance close to the time optimal solution. For example, in this alpha pilot track, the neural network policy can achieve a lap time of 8.14 seconds, and which is very close to the optimal solution at 8.06 seconds. And even though we don't achieve the same performance as optimization-based approach, but reinforcement learning does have its advantage in terms of computation time. For example, we can compare the computation time between our approach and the CPC, which is optimization-based approach. And on this plot, you can see in x-axis is the track length. As the track length increases, the computation time for the optimization increases dramatically. But for the RL, it maintains kind of consistent, even though for very large track. And in addition, we show that the learning-based approach can handle environment uncertainties. As you can see from this plot, we kind of perturb the gate position within some bounds, and then which end up in a totally different tracks. And for the trajectory optimization, even though you shift the position of the gate a bit, the solution will not be valid anymore, and you have to compute the solution again. And in this kind of track, for example, it takes the trajectory optimization 1 hour to solve. And if you want to have different, and you cannot compute this kind of trajectory in real time, and the trajectory compute offline will not valid because of this uncertainty. And instead, using the learning-based approach, our approach is very robust to this kind of environment uncertainty. We test 100 different random tracks, and for different difficulty levels. For example, for the less difficult tracks, which 0.5 means we display the gate position within 0.1% of this bound, and our approach achieves crash rate of 100 or of 0%. And in most difficult level, our still have very high success rate. And the average time of this random checks is still very close to the nominal checks. And here with this, I'll show a video to show how this time optimum flight looks like in this different checks. For example, this is the flight in the Alpha Pilot check. And this is the flight in the Split S check. And this is the flight in the SIM checks. And they, as you can see, the checks layout are quite different, and some have to fly upward and some have to fly forward and have some hairpin curves. And here shows how different combination of the check looks like. So the check are quite random in terms of position and also the orientation of the gates. And here's a visualization of 100 success trajectories of this quadrotor, of these trajectories. And we also show that the neural network policy can handle random checks. And this policy is trained and also evaluated on like very random, completely randomly generated checks. And this shows the complexity of the task and also the complexity of the trajectory. And finally, we deploy this trajectory in the real world. So notice we didn't deploy the policy directly, but instead we generate the trajectory in simulation and then check this trajectory in the real world with an MPC controller. And our trajectory can enable the quadrotor to fly very aggressively. So for example, here it achieves speed up to 17 meters per second. Okay, so in my second project, I'd like to show how can we combine the advantage of policy search with model predictive control. Because in the previous, we still learn end-to-end policy from observation to control command directly. So these are two frameworks, like the two plots of these two different approaches. One's reinforcement learning, which has the advantage of can learn different tasks, can solve different tasks via trial and error, and can leverage large amount of data generated in both real world and also simulation. And on the right-hand side is the model control, which makes use of the optimization, online optimization, also the dynamics of the robots, and it can achieve very good performance in controlling the real, the physical robots. And the question is, how can we combine the advantages of both approaches? And one of the work that inspired our framework is this one, which called policy search for motor primitives in robotics. So in this work, what they do is they encode the motor skills using parameterized motor primitives. And this can be, for example, dynamic movement motor primitives. And by searching in a parameter space of these motor primitives, the robot can discover like novel skills. For example, here, ball in cup or inverted pendulum. And the parameters of these primitives can be learned using imitation learning and also episodic policy search method, which means you don't need to engineer you don't need the demonstration of this task. The robot can learn in a model-free fashion. And then the question is, how can we formulate in the MPC formats? What we do is like we take the model control as kind of parameterized controller. As you can see from here, here is the standard optimization problem in trajectory optimization or in MPC format. And here you have some state actions and some references, and you also have some unknown parameters. And this kind of unknown parameters is highly dependent on the task you have. It can be, for example, very simple example is the weight of your cost function. This can be considered as unknown parameters, which are normally defined by human expert. it can be also other parameters that affect the performance of your optimization. And if we take this as unknown parameters, and this kind of MPC optimization can be considered as like black box optimization, and by changing the parameters, the MPC will have different outputs. And so how do we find the optimum parameters for the tasks? So we can model these unknown parameters as kind of probabilistic distribution, for example, a Gaussian distribution. And then we can formulate the search of this kind of unknown parameters as probabilistic policy search. And here the parameters are modeled as kind of distribution, and we consider this as policy. And this policy is represented as pi, and the parameters of the policy is theta. And by sampling from this policy distribution, we get some like samples. And given these samples, MPC outputs some trajectories. And we evaluate this trajectory using this so-called E, like can be a reward function, some high-level reward function. And then our objective is to maximize the reward function for this task in this framework. And with this objective, we can then solve this probabilistic policy search using weighted maximum likelihood. And it has the advantage of having a closed form solution for the parameters of for the policy parameters. And we later extend this idea to not only learn some fixed parameters, but also we can also learn kind of function approximation, which maps states into the parameters. And so we can learn, for example, Gaussian linear policy for state-dependent parameters. In addition, we can also learn a neural network policy for some high-dimensional state representation, high-dimensional state-dependent parameters. And combine these two frameworks. This top one is called high-level policy, which is used for making high-level decisions, and MPC is used for low-level controller. And with this idea, we apply this framework, policy search for model predict control framework, to the task of Agile drone flight. And the task is to learn to fly through dynamic gates. So here we have, for example, randomly initialized quadrotors, and we have a moving gate. And the gate, for example, is a pendulum, and it's released from randomly initialized an angle, and then it oscillates freely on the between left and right. And our task is to fly through the center of the gate and also reach a goal position behind the gate. And we can define this problem in MPC in our trajectory optimization way. But here, the problem is like, we don't know when should we fly through the center of the gate. So which means we don't know the time. If you don't know the time, when should you fly through the gate, then you don't know where you should fly through the gate. And also, if you don't know where you should fly through the gate, you also don't know when you should fly through the gate. It's like chicken and egg problem. And what we do is we formulate this time variable as unknown parameters and put it into the previous policy search for model predictive control framework. And by define a reward function which evaluates the output of the trajectory of the MPC, which means if at this sample time, if the position of the quadrotor is flying through the center of the gate, then this time, this reward for this time is higher than the time that cannot fly through the gate. And we optimize the parameters of this time variable using policy search methods. And here we show that our approach can manage to control simulate quadrotor to fly through the gate, regardless of the initial position of the quadrotor and also the initial position of the pendulum. So here we have a neural network policy which constantly updated the time when should the quadrotor fly through the gate, And given this time variable, an MPC controller is optimizing, predicting the trajectory, as you can show as this red dot, for these maneuvers. And not only that, not only can we predict like one variables, we can also predict like multi-dimensional variables. In this case, is flying through like a sequence of moving gates. And here we have 3 gates, and we have a neural network policy which predicts the time to fly through each of these gates. So for example, here for the first gate, the time is 1.2 seconds from here to here, and the second gate is somewhere like 2.2, and the last one is around 3.0 seconds. And given this time variable, the MPC can find the trajectory. So we can also deploy this in a like completely unknown environment. So here is like a track of sequence of moving gates, and the task is to fly through all these moving gates given the observation of the quadrotor state and also the state of the moving gates. And as you can see, our quadrotor can successfully control it and fly through all the gates. And also we show that this approach can be deployed in the real world. And here is a different angle to visualize this maneuvers. Okay, so with this, I would like to conclude my presentation. And what we have shown in this talk is like reinforcement learning can achieve near-term optimal solution in the trajectory planning. And it has the advantages of scalable to complex environment and robust to environment changes, which is very difficult for optimization-based approach. And we also show a new framework called Policy Search for Model Control for learning-based control. And we show this framework can be used to handle very dynamic environment. But still, the work I show has its limitations. So it still relies on very accurate estimation of the quadrotor states, which is very difficult in the real world applications. So some discussions is reinforcement learning holds the promise to address some of the challenges for the real world drone agile flights, and how to deal with dynamic obstacles is still an open research questions. Future work can be includes vision-based flight and also multi-agent intelligence, like in a cooperative or in a competitive fashion, and also to deploy the system in a dynamic environment. And what we need is because IO like need a lot of samples, and what we need is simulators, better simulators, and also benchmark comparisons for the tasks, and well-organized competitions to incentivize the community to work together to solve the problem. And we have open source our simulator called FlightMap, which is a flexible quadrotor simulator that combines Unity for photorealistic rendering and also quadrotor dynamics to simulate the quadrotors. And this simulator is fully open source, and you can find it via this link. And finally, I'd like to also mention the Dodge Drone Challenge we are organizing in this year as ICRA. And the task here is to fly from point A to point B, at the same time avoid moving obstacles in between. So as you can see from this video, is an algorithm we developed in our lab. It takes the depth image as input, and a neural network policy is controlling the drone, and this neural network is trained using reinforcement learning, model-free reinforcement learning, and it successfully fly the drone and also avoid obstacles. And if you are interested, you can also participate in this challenge, and you can get a schedule for the winner. And thank you. I would like to thank you for your attention.